Welcome to welcome to lecture 4.1, the first lecture from chapter number 4. In this chapter, we'll study fabrication of CMOS integrated circuits, and in this lecture, we'll study about silicon dioxide's growth and deposition, how it is grown on silicon and how it is deposited if the underlying material is not silicon. If the underlying material silicon dioxide is an insulator, we already know that. And for a MOS, metal oxide semiconductor, for a MOS, the implementation is such that drain and source terminals are implemented on a substrate. This is actually an NMOS, a side view of an NMOS. Drain, source, implemented in P-type substrate, and then we have the silicon dioxide, the insulating layer, and then we have this poly. Poly is actually the gate terminal. We call it poly. We'll shortly know, maybe in the next lecture, why do we call it poly? Why not gate? Right. So we call it gate and poly both, in fact. So silicon dioxide is this insulating material which is used to create an electrostatic field so that minority carriers are pulled up in this channel and the current flow is set up. We already know the theory behind, or the theory behind this MOS, NMOS and PMOS both. Right. So adhesion is excellent for a silicon dioxide material. This means it can be deposited on many different materials that we have in the line, or that we use to implement CMOS ICs. For example, metal, for example, silicon dioxide itself, and semiconductor materials, etc. Right. So it can either be grown on a material or it can be deposited. The difference is that we use the word growth when the underlying material is silicon and we have to convert a very thin top layer into silicon dioxide. And we use the term deposition when the underlying material is not silicon. So first we'll study some techniques regarding growth of silicon dioxide. This means the underlying material is silicon. If we have this silicon bar, and you want to convert a top layer of the silicon bar into silicon dioxide, we will use an O2 flow. A hot oxygen will pass hot oxygen on top of it, and this is the chemical reaction. Silicon in the presence of silicon reacting with oxygen in the presence of heat converts into silicon dioxide. Right. So a very small layer of silicon is also used, and the remaining is oxide to make it a silicon dioxide layer. So a very small thickness of original silicon is also becomes the part of this silicon dioxide layer. So the thickness of silicon dioxide layer, so the thickness of silicon layer, this very small layer that is converted into the silicon dioxide, is almost 46% of the silicon dioxide layer that we finally achieve after this chemical reaction. It's a superb chemical reaction which produces a high quality silicon dioxide, but has some disadvantages. Perhaps the biggest disadvantage of this conversion of top layer of silicon into silicon dioxide is its slowness. The process is very slow, so it takes time. So is there a way we can speed up the process? Yes, it is. If you use wet oxidation. Wet oxidation is a similar process and requires the underlying layer to be silicon. In fact, it is the growth technique. Right. So what we do is we use steam instead of oxygen. Instead of oxygen, we use water. hot water steam passing over silicon converts part of it into silicon dioxide and H2 gas, which is evaporated. So it's a faster process, requires less amount of time to convert the top layer into silicon dioxide. So the both techniques that we have discussed up till now, this wet oxidation technique and the thermal oxide technique and the wet oxidation technique. In thermal oxide technique, we use oxygen, and in wet oxidation technique, we use steam instead of oxygen. They both convert top layer of silicon to silicon dioxide, and they both require the underlying material to be silicon. They both collectively called native oxide techniques. They produce native oxide because part of the silicon which is processed is converted into silicon dioxide, and they require the surface Si should be exposed to the process, right? But we have situations where the top layer isn't silicon and we have to still convert it into silicon dioxide. Maybe this substrate, maybe this is metal or any other layer, and on top of it we have to deposit a layer of silicon dioxide. Silicon dioxide is represented with these diagonal lines. So how would you convert this top layer into silicon dioxide when the underlying material is not silicon? So of course we cannot use the native oxide technique. We cannot use oxygen to pass over it. Neither we can use steam because the underlying material silicon isn't there to react with. So we should use some technique based on vapors of the gas, and we call it CVD, chemical vapor technique, chemical vapor deposition. No underlying silicon, so what you do is you use silicon hydride. So we have these silicon hydride, maybe these red vapors are silicon hydride vapors being available on top of it. So we are dropping silicon dioxide vapors on top of the material, and maybe I cannot use different color. I wish I could. Maybe we can use, oh no, we cannot use, right? Okay, we can use a different shape for those, maybe these triangular shapes. These triangular shape atoms are of oxygen, so we are falling these atoms, these vapors, oxygen vapors and silicon hydride vapors from the top, and when they fall on the surface there is a chemical reaction. Silicon hydride plus oxygen form silicon dioxide and steam. The water is in the form of a steam gas. This water is in the form of gas. So we have silicon, we have this top layer converted into silicon dioxide. This technique is also called LTO technique, low temperature oxide, because to implement silicon dioxide using this technique, we don't need a high temperature like we required in case of native oxide. In case of these native oxide techniques, we require a temperature that is between 850 to 1100 degrees centigrade, which is very large, a very high temperature, 850 to 1100 degree centigrade. So this technique is also called LTO, right? Since this is not the only option of getting silicon dioxide on top of it, we can choose another material. Silicon dioxide, in fact, is not the only material that can be used as insulating material. Instead of silicon dioxide, we can have another insulator. We call it silicon nitride. Silicon nitride is also an insulator like silicon dioxide. So in order to convert this top layer into silicon nitride, we use silicon hydride in the presence of ammonia. This is ammonia gas, NH3. Silicon hydride, when reacts with ammonia gas, converts this top layer into silicon nitride, and hydrogen gas is emitted out. So silicon nitride, Si3 and 4, silicon nitride is this. Silicon nitride, Si3 and 4, they are strong barriers to most atoms, even stronger than silicon dioxide. So in many cases, they are better insulators than silicon dioxide. So what is their application? Silicon nitrides are ideal for overglass applications. Overglass is a kind of plastic coating that is used on the outer side of the chip. Once we have developed the chip and we want to pack that chip into under a plastic material, under a protective sheet that is insulator, the whole IC is converted, is packed in a chip. The whole IC chip is packed in a coating that we call overglass, and most of the times overglass is made up of silicon nitride. So we'll continue studying more about fabrication techniques in our upcoming lectures. Thank you.